Good evening, everyone. Again, thank you. My name is David Malpas. I am employed by the Antarctic Support Contract as a construction manager and modernization for science lodging project at McMurdo Station, where I'm currently deployed. At this point, I have spent 5 summer seasons, 2 winter seasons, 1 autumn shoulder season based out of McMurdo, where I started as a carpenter, then a construction superintendent, and now construction manager. I have also spent 3 seasons at Summit Station in Greenland at the top of the Greenland ice sheet, and 1 summer at Toolik Station on the north slope of Alaska. I just realized that I accidentally loaded the wrong presentation, so I'm going to have to bear with me a little bit on this one. Oops. Anyway, where are the polar regions? I usually lay this out for the sake of discussion going forward, because over the course of my career in polar operations, I've had many people ask what Antarctica is like up there. So up top here, we've got the Arctic region and the geographic North Pole. It's an ocean with sea ice, and therefore it is at sea level. There are polar bears in this region, but no penguins. Down at the bottom is the Antarctic region, where I currently am, and the geographic South Pole. This is on land and glacial ice, and the South Pole itself is approximately 9,300 feet in elevation, and there are penguins on the continent, but no polar bears. During the period of time in polar exploration known as the heroic or golden era, some explorers like Robert Falcon Scott or Ernest Shackleton would take scientific measurements and obtain biological and geological samples, then return home with them. These actions sowed the seed for polar research in the decades and century to come. In 1955, the United States Navy embarked on Operation Deep Freeze. This was a major push to develop a permanent presence in Antarctica in preparation of the International Geophysical Year. It involved the establishment of 7 research stations in Antarctica, including McMurdo and South Pole Station. The International Geophysical Year followed in 1957, which was an 18-month period where nations committed research into 14 earth science disciplines. The National Science Foundation was created on May 10th, 1950, to promote the progress of science and to advance the national health, prosperity, and welfare of the United States. The Antarctic Treaty was signed by 12 countries on December 1st, 1959, and this reserved Antarctica for scientific research. As of today, there are 58 signatory nations. On December 1st, 1959, Dwight Eisenhower signed a presidential directive that gave the NSF responsibility for almost all U.S. Antarctic operations, now known as the U.S. Antarctic Program, or USAP. Now I'd like to give a quick overview of the stations that the United States operates in polar regions. The U.S. operates 3 research stations in Antarctica. These are Palmer Station, south of the Drake Passage, Amundsen Scott South Pole Station, and McMurdo Station, south of New Zealand. Each of these stations provides its own unique research opportunities and logistical challenges. Palmer Station, named after Nathaniel B. Palmer, who has been recognized as the first American to lay eyes on the continent of Antarctica. Amundsen Scott South Pole Station has been continuously operated since 1956 and is named after Roald Amundsen, the leader of the first expedition to make it to the South Pole, and Robert Falcon Scott, the leader of the ill-fated second expedition to make it there, and McMurdo Station, which is named after McMurdo Sound, which it is on the coast of, and that is an international logistics hub for Western Antarctica, and helps support not only the United States program, but also Italy and South Korea as well. Palmer Station is the smallest of the 3 Antarctic stations, with a summer population of about 45 and a winter population of about 20. Palmer was constructed in 1968 and is primarily focused on marine biology and long-term ecological research, along with oceanography, glaciology, and astrophysics research also being conducted there. South Pole Station has the newest primary structure of the 3 U.S. stations. Construction of this building, which was the 3rd generation structure, began in 1999 and completed in 2008. It has a summer population of about 150 and a winter population of about 50. Most of the research conducted here is astronomy, astrophysics, earth sciences, atmospheric science, and meteorology, and is the home of the South Pole Telescope. That brings us to McMurdo Station, which has the largest population on the continent. In summer, it houses up to about 1,100, while in the winter, it will have about 150. Most of the research conducted is in the area around McMurdo, not usually directly out of, unless it happens to be sea ice based. That said, it has facilities to store ice core samples amongst other lab facilities for just about any field of study you could imagine. Though the primary subjects are glaciology, long-term ecological research, atmospheric, geology, and astrophysics. Also, a little fun fact, the galley or kitchen at McMurdo serves about 148,000 meals annually. Up north in the Arctic program, we have Toolik Field Station, which is north of the Brooks Range, about 370 miles north of Fairbanks. The station population in the summer hovers around 150, but drops to about 30 in the winter. This station is operated jointly between the University of Alaska Fairbanks, the Institute of Arctic Biology, and the National Science Foundation. Most of the research conducted here is Arctic biology, but there's also geology, atmospheric physics, and climate research being investigated there as well. Summit Station is located approximately 220 miles inland from the east coast of Greenland and 310 miles from the west coast at 10,550 feet on the Greenland ice cap. It has an average summer population of about 45 and in winter about 8. It was established in 1989 for the Greenland Ice Sheet Project, where they cored 10,017.8 feet into the glacier, which at the time was the deepest ice core ever recovered. Most of the research conducted here is atmospheric and climate-based, with some additional research conducted in astrophysics and glaciology. I get asked sometimes, what is a field camp? Field camp is a seasonal or temporary camp established in remote polar locations to support scientific research or logistics. After all, the purpose of going to these cold, remote places is so scientists can conduct research in the field. To conduct this research, they need a warm shelter and to have warm meals. Keep in mind that most of these environments are not just cold, but also quite austere. Humans are not meant to live in these places, especially long-term, and therefore simply existing there for any period of time can be quite dangerous. These camps consist of tents, portable modular structures, or a combination of both to provide food, shelter, and communications for research teams to safely conduct scientific work. Some camps are helicopter supported and some camps are fixed wing supported. This depends on how far away they are from the station. Helicopter supported field camps are typically less than 100 miles from McMurdo Station, though there have been exceptions to support science or recovery rescue missions that have pushed much further than that. Helicopters used in the Antarctic program are Bell 212s and Eurocopter AS-350s, but in the Arctic program, they don't need to carry the same amount of cargo, so they use a much lighter duty Robinson R-44. This video shows a prefabricated SIP panel package in sling loads that have been staged for a new field camp building located out at Lake Frixel in Taylor Valley, which is in the dry valleys across from McMurdo Station. This is a Bell 212 hauling out a crate of tools from a group of outgoing carpenters, having already dropped off the orange and blue crate of tools for the replacement team. Oh, apparently that video didn't play. So anyways, fixed wing supported camp is typically going to be further than 100 miles away from McMurdo. The aircraft will either be a Twin Otter, modified C-47 DC-3 airframe called the Basler, which is shown in this photo, or a Lockheed LC-130. Tools and materials are netted in cargo areas or to Air Force pallets. So what's the weather like? Very common question is that. So cold is cold, right? Well, not exactly. Each station or camp has its own unique environment and climate, just like different towns and cities have everywhere else. Some conditions that may affect a station's weather are the season that you're working in, whether it's summer or winter, the elevation, its distance to seawater, the surrounding topography, and the amount of annual snow accumulation are just a few. In this photo I took at Summit Station, it shows an ambient temperature of -52 Fahrenheit and a wind chill of -83. It also has a pressure altitude of 11,194 feet, or more than 600 feet higher than the actual elevation. What are some of the things that we wear? Well, down here, we are issued the Big Red Parka by Canada Goose. It's big, it's bulky, and it will definitely keep you warm if your plane has an uncontrolled landing. If it's your first season in Antarctica, you're required to wear it. That said, if you're working out in the field, eventually you'll develop your own layering system that works individually for you. This is something a little bit more like what I wear. Typically, this consists of Carhartt bibs, an insulated boot like Baffin boots, a good mountaineering jacket, and several other layers underneath, a beanie, sunglasses, or goggles, depending on wind conditions, and a neck gaiter works pretty well and covers most temperatures. While there's some baselines that we have to work from, eventually everyone figures out what system works best for themselves. Other things we might keep on us are hand warmers, an extra neck gaiter, extra goggles, extra gloves, because those things have a tendency to blow away on you, snacks and water. Some of the projects that I've supported, well, down here at McMurdo Station, NASA operates a facility called the Long Duration Balloon Launch Site. This is where large balloon payloads are launched with a balloon that will expand to the size of a football field. These payloads are often used for atmospheric or astronomical research. The buildings that house these payloads, which are the two large buildings on the left in this photo, need to be heated, but they are also seasonal. So all of the utilities for these structures need to be connected and disconnected every year, and the buildings are stored on a winter berm or small hill to reduce snow drifting and reduce the likelihood of damage occurring. Here's a photo of one of the payloads on its way to being launched. These can be over 20 feet tall and weigh a couple thousand pounds. I've also helped repair the Super Dual Auroral Radar Network, also known as Super Darn, at McMurdo after a winter storm caused some damage to it. In this photo, I'm at the top of the 75-foot crane and strapped in, about to make some repairs to the wire. Super Darn consists of 41 high-frequency radar stations located in both the northern and southern hemispheres, and it's used to map high-altitude or high-latitude plasma convection in the ionosphere. Here's an example of the type of information they're able to compile about aurora using this radar network. In 2015, I helped construct a deployment shelter for a robotic project called Artemis. Artemis was a semi-autonomous robot that was able to navigate around underwater, raise scientific sensors into contact with the ice overhead, collect water samples, and dock with surface recovery equipment. This is a photo of the shelter package that we brought out onto the sea ice prior to construction. This project required a 52-inch hole be drilled 5 feet into the sea ice, where a corrugated steel pipe was sleeved and fixed into position, which would enable the team to keep unfrozen with a warm air blower. Here's a photo of the Artemis robot during one of the deployments. This robot was also researching what could be done for a possible future mission to Europa. Because the robot needed to fit through the 52-inch hole, it had to be hoisted and recovered vertically using a gantry system that we assembled on site, which you can also see in this photo. This is a photo of a rack tent that we built on the ice. This is a modular tent system that is used all around Antarctica to provide researchers with a heated shelter. These tents use a diesel-fueled heater to keep the interior at a reasonably comfortable temperature. You can see the fuel tank and exhaust flue in this photo. Tents are often used for researchers because their studies are typically performed during the summer season and the need for a permanent structure is not necessary. Some ecological research has been going on for decades down here. These projects fall under the auspices of long-term ecological research, or LTER, and will provide yearly data points for things like penguin and seal studies, measuring water flow into frozen lakes, or glacial studies. This is a photo of my wife, Janae, connecting a sling load to the underside of a hovering Bell 212 so it could be flown back to station at the end of the season. Shackleton. This is Shackleton Deep Field Camp. It was located in the Transantarctic Mountains at 85 degrees south latitude. The purpose of this field camp was to collect geologic samples in ice-free conditions. The duration of this camp was 3 years, and it involved disassembling a helicopter, loading it onto an LC-130, flying it out to the camp, unloading it, and reassembling it. This was much faster and safer than having the researchers climb the mountains individually to collect these samples. I've also helped support the West Antarctic Ice Sheet Divide, or WAISE Divide. This was an 8-year project to drill ice cores. This area was chosen because it has a moderate ice accumulation zone located on a ridge between the Ross Sea and Weddell Sea drainage basins. The purpose of this project was to investigate environmental conditions during the last 68,000 years. This is the location of the deepest ice core drilled by the United States at 3,405 meters, or 11,171 feet, and is also the location of the first replicate ice core ever drilled. Up in Greenland, I helped support the RNOG, or the Radio Neutrino Observatory of Greenland. Neutrinos are elementary particles which get their name from being electrically neutral, and because the resting mass is so small, it was long thought to be zero. Neutrinos are created through various radioactive decay processes, such as during beta decay of atomic nuclei or during a supernova. They pass through normal matter unimpeded and with no detectable effect. Researchers have been able to detect and measure these particles using a three-dimensional sensor array in glacier ice. Multiple sensors are arranged on a long cable like a string of pearls and lowered into holes drilled into the glacier. The first one ever created was installed at South Pole Station and is called IceCube. I assisted the drill team that was installing the new array of sensors up at Summit Station in 2021. So that's the quick rundown of some of the polar research stations that the NSF operates and some of the seasonal work that's performed there. Now I'd like to discuss some of the larger projects I've worked on. Up north at Summit Station, it's located at approximately 10,500 feet on the Greenland ice cap in what is known as an accumulation zone. An accumulation zone is important to glaciology because it's an area where snow collects and then spreads out from. And one of the primary reasons the site was originally chosen by the Greenland Ice Sheet Project in 1989. Approximately 3 feet of snow accumulate at Summit every year, and because of this increase in apparent grade, structures either need to be lifted or relocated every few years to stay on the surface. That was an aerial view of Summit Station, and I unfortunately went forward. I don't know if I can go back. There we go. Okay. At the very top is a small isolated dot. This is the Atmospheric Watch Observatory, also known as AWO. Because Summit is surrounded by snow for more than 200 miles in any direction, it has some of the cleanest air in the northern hemisphere. The AWO is an elevated structure that samples air and measures particulates in the part per billion. When you're going to put up a structure in an accumulation zone, your basic options are an elevated structure or a surface structure. Elevated structures are more complicated and have a higher initial cost. The main advantage is that elevated structures scour snow underneath and therefore don't need to be reset as often. Surface structures typically have a lower initial cost and are easier to set up. However, they create snow drifts and increased accumulation around the building and station. This results in requiring more frequent structure resets and snow removal by heavy equipment. This photo helps illustrate the difference between an elevated structure like the big house on the left with the white ray dome on top and the greenhouse surface level dorm facility on the right at the other end of the fog bow. Both types of structure have their unique advantages and disadvantages depending on anticipated building purpose and life. In 2018, the primary structure on station, known as the Big House, needed to be lifted. The Big House is the primary operations building on station and was estimated to be about 100,000 pounds. It houses the office, satellite and radio communications, the galley, and laundry room. There was a pre-existing hydraulic lift system that had been used for about 20 years. That lift system involved welding 20-foot long, 10-inch square steel columns to the existing ones, then crawling the lift system up the new vertical additions. Unfortunately, after crawling up almost 80 feet, they were slowly being compressed inwards due to glacial movement and would no longer move vertically. So this project required a second auxiliary building lift system that would enable us to support the structure, cut the existing columns, lift the building, bolt on new adjustable footers to the white existing columns, and then lower the building back onto those columns. This is the auxiliary lift system that we used. It was fabricated by a small company out of Regina, Saskatchewan called Failsafe House Lifting. This was a test build of the lift system prior to sending it up to Summit. The system utilized 6 lifting towers, 3 on each side of the building. These towers supported a secondary beam on each side of the structure that ran through the towers and rested on the lifting cradle. 5 primary beams were placed on the secondary beams. Their locations would be dependent on internal weight loading of the building, with most of the weight falling underneath the ray dome due to the communications and kitchen equipment being located on that side. Primary beam support jacks were clipped to the underside of the secondary beams prior to lifting, so when the building was raised, the support jacks would be lifted with it. Once the structure was fully lifted, the support jacks were set on footers to distribute the load and pinned for safety, providing mid-span support of the primary beams. This is the interior cargo bay of a Lockheed LC-130H. Almost all the materials, tools, heavy equipment, and modular structures have been flown up to Summit using one of these aircraft. In fact, all 24 million pounds of the South Pole Station were flown down, 26,000 pounds at a time, over a total of 924 flights. This photo shows the 80-foot tracked aerial lift being secured by the loadmasters down in Kangerlussuaq, Greenland, before making its way up to Summit. And this is the track loader offloading pallets of material and cargo from an LC-130 at Summit. There are only 7 of these aircraft in existence, and they're operated by the New York Air National Guard out of the Schenectady County Airport. They're also the largest ski-equipped aircraft in the world. I'm going to skip through a couple of these photos. This was a test build or a test run of that lift system, and that snowblower there is called the Snow Beast. And that's a 6-cylinder diesel-powered snowblower, so it would definitely help for some of those snow storms that you get in New Jersey. This was assembling the utilities on the underside of the structure. We had 480-volt connections that were able to disconnect the electrical to the building, and we also had to disconnect the water supply as well as the wastewater system. Let's see, this is an aerial photo of the completed Big House lift with its fully supported by the fail-safe system. You can see the additional primary beams on the far side of the to help support the additional load. Also, you can see the primary jacks supporting the mid-load span. When lifting a structure, you'll find out everything you need to know within the first couple inches. In this case, we discovered that the motors on the lift towers were running at different speeds despite running from the same generator. So we had to add two 2.5 kW generators to power all 6 of the lift towers evenly. And this was due to voltage drop at the far points, reducing motor speed. And I'm going to speed through this one real quick. Again, I apologize. I managed to load the another talk that I give for polar construction, so bear with me. So this was relocating one of the ground structures up at Summit. And that shows the difference between the two structures, the elevated structure in the back and the reset dorm facility in the front. And this is the future of what they're having up at Summit Station. This is a self-lifting platform. So each of those legs has the ability to be raised 10 feet. And so what would happen is once the structures need to be reset, they will dig out each one of those legs, the footer on it. They'll lift each leg individually, backfill underneath with that large snowblower, the snow beast, and then reset all of the legs. Once all 12 legs are reset onto the snow surface, then the structure will extend again and the entire building will be raised like that. This is what I'm currently working on. This is the part of the AIMS project, or the Antarctic Infrastructure Modernization for Science. This is an effort by the National Science Foundation to update critical structures on station to reduce infrastructure and maintenance costs over the next 75 years. Almost all of the buildings in McMurdo were built when the U.S. Navy oversaw operations, and they weren't constructed with long-term lifespan or energy efficiency as a thought. Now some of these buildings are quite difficult to keep warm, and the cost to keep them heated continues to increase every year. The end result has been that less money can be used to fund scientific research because they're simply trying to keep the buildings warm at this point. So the NSF has decided to start with 3 structures. A new vehicle and equipment operations building that will house light and heavy equipment repair facilities. They also have started in addition to an existing building that will house updated IT and communications equipment. And lastly, there's the lodging project, which is what I'm currently working on and is shown in this rendering. The lodging building is a 49,500 square foot building that will be able to house 285 people. It's a fixed position elevated steel frame structure with precast concrete slab floors. It's elevated to allow wind to scour snow underneath, but it doesn't need to be adjustable because McMurdo isn't in an accumulation zone. The entire structure is insulated with graphite polystyrene, or GPS SIP panels. GPS foam can increase R values by about 20% more than standard expanded polystyrene, making it perfect for polar applications. In the case of the lodging building, the understory is insulated to R70, while the exterior wall and roof assemblies are insulated to R60. The wall panels are anodized aluminum skinned foam panels and are also insulated to R10, and they provide additional insulation besides just a decorative anodized finish. There are 3 redundant boilers, each of them being 3 million BTUs. But it's also connected to the waste heat loop coming from the power plant generators to help offset heating costs as well. The next few photos are what life is like as a polar contractor to help support scientific exploration and science support. Just getting to work can be a challenge. Once you're there, the remote isolation can be a challenge for just about everyone at some point. While you're deployed in these places for month after month, you miss birthdays, anniversaries, weddings, Thanksgiving, Christmas. If a family member or friend suddenly falls ill or passes away, you don't have the ability to be there with them. When you're out in the field, the only connection you have with family and friends is often the satellite phone. Here's a photo of my commute to work up to Greenland. Many of these locations are so remote, the closest human beings besides the ones you're working with are the ones flying overhead and on the International Space Station. For example, seeing a plane in the winter at McMurdo is such a bizarre thing. People run to the windows to witness the sight of the red blinking light off in the distance. Obviously, the cold can be a major issue. This was a minus 65-degree day in September that had a wind chill of minus 105 Fahrenheit. I ended up with a little bit of frost nip on my nose just walking to work that morning, and I have to now be concerned about that for the rest of my life as cold injuries are permanent. Whenever there's wildlife, you are not permitted to interact with it, so that might stop work for a little bit. Here's a group of Adelie penguins molting on Hut Point, where Discovery Hut is located. Discovery Hut was established by Robert Falcon Scott during his discovery expedition, and it still exists down here today. It's always fun when you have to stop work because a curious group of penguins waddled up to check you out. Of course, there are also times when you don't want to interact with the wildlife. This was when a polar bear stopped by Summit Station in 2018 for the first time since the station had been constructed. This fuzzy girl shut down station for 2 days because no one was allowed to, or wanted to, for that matter, go outside any of the hard-sided structures. This is setting up a rack tent, and this is the beginning of what a storm was. So we're trying to beat the winter storm that was coming in, and we're racing against the incoming weather. This is what we dealt with the next day, and we started to deal with whiteout conditions. At deep field sites in Antarctica, researchers and support personnel sleep in tents. Each tent is identified on a grid so everyone can be accounted for. And the flag line has a rope to help you get around if you absolutely need to in a total whiteout. So that flag line is what we ended up following, so that way we could get to breakfast that morning. And needless to say, we did not get much work done that day. And the next day, this is what we found when the storm was over. There was a small gap in the bottom of the weather stripping on this bulldozer, and it caused the entire cab to be filled. Things like this can certainly cause delay that most places don't have to deal with. This is the inside of a Scott tent. Sometimes the weather forces you to stay in bed much longer than you had anticipated. This is one of my fellow carpenters with me in a Scott tent at 9,500 feet on the side of Mount Erebus, which is the southernmost active volcano in the world. We had been flown up to this location a week earlier to acclimate for 2 days prior to being bumped up to another spot called Lower Erebus Hut to perform some maintenance. Weather ended up keeping the helicopters grounded, so 2 days slowly turned into 7. After a while in these conditions, morale can start to decrease, so it really helps to have a great group of people to work with. These are the types of people who dig deep and get the group laughing no matter what, or how exhausted everyone is, how cold it is, or how much all you want to do is go home and take a hot shower. Let's see. This was a situation where just finding what you wanted to work can be difficult. This was in 2021 when we, up at Summit Station, we weren't able to do any heavy equipment snow clearing the year prior. So these two gentlemen were digging out a sewer pipe to overhaul it. And it ended up taking 2 days for them to dig down this far. In case anyone has construction experience, this did not require any shoring up because the Cold Research Engineering and Environment Lab, or CREL, has determined that it's possible to dig down 150 feet into glacier ice without requiring any additional safety shoring. This is up at Summit. Sometimes 24 hours of daylight can be a challenge to work with over the weeks and months. At first, you get a boost of energy, but after a while, it affects your sleep pattern and circadian rhythm. You can get tired of seeing the sun, believe it or not. Over the course, of course, there's also some great things about the sun in polar regions. These are atmospheric optical effects, or adoptics, created by refraction of light through ice crystals. In this case, it's a 22-degree halo around the sun with some parhelion or sundogs on the left and right, and a circumzenithal arc up at the top. It's also 12:30 in the morning. This is the U.S. Coast Guard icebreaker Polar Star. It's tasked with clearing a channel into McMurdo Sound to allow the annual fuel and resupply vessels access to dock up at the ice pier. When you're ordering materials for a project that you need a year later and it requires a Coast Guard icebreaker to help get them to the site, you really need to make sure that your estimates are correct and you really know that you're kind of extended away from other people. And getting materials to these places can be a challenge unto itself. Most of the materials and supplies making their way to McMurdo or South Pole need to be specified, purchased, loaded into a container, put on a vessel in Port Hueneme, California, and shipped to Antarctica. When they make it to the ice, they're offloaded at McMurdo, inventoried, and redistributed. If it needs to make it to the South Pole, it will either be palletized for air transport by LC-130 or put onto inflatable mats and dragged down on one of the 3 South Pole traverses that also brings fuel down to South Pole Station every season. When I'm asked with all the challenges why I like to do what I do, it's a bit difficult to answer. I enjoy a challenge working in beautifully austere environments, and I'm certainly a fan of what's called type 2 fun, which is maybe not so much fun in the moment, but it ends up being fun later on. One of the things I really like about my job is the logistical complexity of working in these places to achieve a goal. But what really makes me come back over and over again is the people. These environments attract the most amazing people who like to look at adversity and just laugh. The polar regions are an important barometer into how our Earth is responding to climate change. They can tell the stories of Earth's past through ice cores, or what things currently look like through atmospheric air sampling. The scientific research done in these areas help provide us with the information about the origins of the universe and show us that life can exist in absolutely inhospitable conditions for hundreds of thousands of years or more. These are truly amazing places. I'm both lucky and honored to have an opportunity to not only support these research teams and to do my little part to help further science, or advance the research at the cutting edge of science, but to also have had the opportunity to share these experiences with all of you. Thank you all very much for taking the time to listen to my presentation, and I look forward to hearing your questions. Thank you.